The integral of 2 over x squared plus 1 over x minus 5 root x plus 7 over the cube root of x to the fifth dx. Let's start by just rewriting this expression inside of the integral so that it's easier to integrate, mostly using power rules. All right, so first of all, the 1 over x squared, we could move this to the numerator or get rid of the fraction by rewriting it with a negative exponent. So 1 over x squared is the same as x to the minus 2. 1 over x we're going to leave alone because that one is special. That's going to become a logarithm, right? Root x, well, the root becomes the denominator of the fraction for the exponent. So root x is x to the 1/2. And now this one, 7 over the cube root of x to the fifth. Well, the power is 5. The root is a cube root, so that goes in the denominator of the fraction for the exponent. And since this is 1 over the cube root of x to the fifth, if we want to bring it up, we negate the exponent. Okay, now we're all set to integrate just using the power rule. All right, so for the first one, 2x to the minus 2, we're just going to add 1 to the exponent. So negative 2 plus 1 is negative 1, and divide by that same number. Antiderivative of 1 over x is ln of the absolute value of x. For x to the half, we add 1 to the exponent. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2, and then divide by that same number. And same thing here. Negative 5/3 plus 1 is negative 5/3 plus 3/3, which is negative 2/3, and then divide by that same number. And don't forget to add your arbitrary constant because it's an indefinite integral. Okay, now we're just going to simplify all this stuff, especially these complex fractions. Remember that we could just, when you divide by a fraction, you could multiply by the reciprocal. So we're going to flip these and bring them up. But let's do them all, each term, step by step. So x to the minus 1, we could rewrite as 1 over x. So in other words, we could bring this to the denominator with an exponent of 1, and we don't have to write the exponent of 1. And I just brought the minus sign out front. So minus 2 over x. ln absolute x will leave. Again, the 3/2 we're going to flip and multiply. So that becomes 2/3. 2 times 5 is 10. And x to the 3/2, the 2 in the denominator, we can make a square root. Again, here we're going to flip and multiply this to negative 3/2 times 7. 3 times 7 is 21. And we could get rid of the next negative exponent here by moving this to the denominator. And the 3 becomes the cube root. The square stays where it is because it's the power. Okay. The integral from 0 to pi over 12 tan squared 3x dx. Okay, now there's no elementary antiderivative for tan squared 3x without doing a little bit of manipulation. We're going to use the Pythagorean identity that involves tan squared and secant squared. Most of us probably remember that such a thing exists. I always forget exactly whether it's one minus secant squared minus 1. So I always start with the one I remember, which is cosine squared x plus sine squared x equals 1. And then I divide through by cosine squared x, right? And we get cosine squared x over cosine squared x is 1. Sine squared x over cosine squared x is tan squared x. And 1 over cosine squared x is secant squared x. This gives us the relationship between tangent squared and secant squared. And since we want to replace tan squared by an expression involving secant squared, I'm just going to bring the 1 over to the other side of the equation, subtracting 1 from each side here. Okay, so now I can replace tan squared by secant squared minus 1. And of course, we have to replace x here by 3x. So there we go. Now, these are both integrals we could do. Right? The antiderivative of secant squared x is tan x. Now, because of this 3 here, we are doing a little substitution. This one's simple enough that I think we could just do it in our head, that if u were 3x, then du would be 3 dx. So we need the 1/3 to make up for that. Okay, so this just becomes 1/3 of tangent 3x. And an antiderivative of 1 is x. And we're going from 0 to pi over 12. So now we just go ahead and plug in the pi over 12, subtract and plug in the 0. right? 3 times pi over 12 is pi over 4. So we get 1/3 tan pi over 4 minus, plug in the pi over 12 there, and then subtract and then plug in the 0 here and here. Tangent of 0 is just 0. And of course, 0 just gives us 0. All right. And the tangent of pi over 4 is 1. So we get 1/3 minus pi over 12. And then just to get this as a single fraction, I'll multiply this by 4 over 4. So we have 4 over 12 minus pi over 12 is 4 minus pi over 12. Okay, the integral from 0 to 2, 3x squared dx over the square root of 8 minus x cubed. Okay, we're going to do a substitution here. If we let u equal 8 minus x cubed, then du is, well, the derivative of this is negative 3x squared times dx. Okay, we're missing the minus sign here. We have 3x squared dx, but we need the minus sign, so we put it in, which is equivalent to multiplying by -1, and then we multiply by -1 on the outside to cancel it, right? -1 times -1 is +1. Okay, now we're ready to figure out what the new limits are going to be. When x is 0, we get u is equal to 8 minus 0 cubed, which is 8. And when x is 2, we get u is 8 minus 2 cubed, or 8 minus 8, which is 0. Okay, so we could go ahead and replace 0 by 8, 2 by 0, and then du is negative 3x squared dx, so all this is du, and u is here, so it's 1 over the square root of u, which is 1 over u to the half, which is u to the negative a half. Okay, great. So I'm going to leave the minus sign, and then we add 1 to the exponents. That's u to the negative a half plus 1, or negative a half plus 2 halves, which is 1/2. And then remember, we divide by that same number, which is a half, or equivalently, multiply by the reciprocal of a half, which is 2. Okay, now we're ready to plug in the limits. 0 to the half and 8 to the half. Okay, all multiplied by -2 on the outside. So 0 to the half is 0. So it's just -2 times -8 to the half, which is 2. The negative times negative is positive. So it's just 2 times the square root of 8. And since 8 is 4 times 2, we could simplify that root as root 8 is equal to 2 root 2. So we get 4 root 2. The area of the region in the first quadrant, bounded by the graph of y equals x squared root 1 minus x cubed, the line x equals 1, and the x-axis is, well, first thing to notice here is that this is just going to be a straightforward integral. Notice if we plug a 0 in for x, we get 0. And if we plug a 1 in for x, we also get 0. 1 minus 1 cubed is 1 minus 1, which is 0. And between 0 and 1, this is completely above the x-axis. It's always going to be positive. A number between 0 and 1 squared is positive, and a number between 0 and 1 makes sense in the square root because we're subtracting 1 minus something between 0 and 1. So all this is going to be positive when we're strictly between 0 and 1. So this is just going to be an integral from 0 to 1 x squared root 1 minus x cubed dx. Now, if this dipped below the x-axis, if anything became negative between 0 and 1, we'd have to be a lot more careful and probably draw the picture and see where this thing hit the x-axis. But in this case, it's a simple case because it's always above the x-axis. All right, so let's try to do this one a little more quickly than the last one, and then we'll regroup and fill in some of the steps just in case anyone is confused. But basically, there's a little substitution here. U equals 1 minus x cubed, and du would be negative 3x squared dx. So we're missing the -3. So we're going to need to put in a -1/3. And then it's 1 minus x cubed to the, well, 1/2 plus 1 is 3/2. Divide by that same number, 3/2, or equivalently multiply by 2/3. And that's going from 0 to 1. So you want to practice being able to do these substitutions in your head like that quickly. Again, if you were confused by that, after I finish, I'm going to come recap the substitution. Okay. So now this is just equal to 2/9, right? Because when you plug in a 1, you get 0. And when you plug in a 0 here, you just get 1. Since you're subtracting that, you have double negative, and 2 over 3 times 3 is 9. Okay, and that is the answer. All right, now, just in case you didn't follow all of that because it went too fast, let's fill in a few of the steps. And I'm also going to do the substitution the way I did last time. So first of all, the square root of 1 minus x cubed is 1 minus x cubed to the half, right? The root becomes the denominator of the fraction in the exponent. And we're going to be letting u equal 1 minus x cubed, as I said, so that du is negative 3x squared dx. So all that's missing here, right, we have the x squared dx. We just need the negative negative 3, right? So we're going to put in a negative 3 and pull out a negative 1/3 to make up for it. Okay. Now for the limits, if x is 0, then u is 1 minus 0 cubed, which is 1. And if x is 1, then u is 1 minus 1 cubed, which is 0. So we could go ahead and change those limits. All right, so the 0 becomes a 1, the 1 becomes a 0. And then over here, negative 3x squared dx is just du, and 1 minus x cubed is u, so this is u to the half. Okay, now we could go ahead and integrate, leave the negative 1/3 where it is, and we add 1 to the exponent. 1/2 plus 1, or 1/2 plus 2/2 is 3/2. And again, dividing by 3/2 is the same as multiplying by 2/3. And we get negative 2/9 times, well, 0 to 3/2 is 0, 1 to the 3/2 is 1. And just as before, we get 2/9 as our final answer. Gasoline is dripping out of a gas pump, filling up a bucket. The amount of gasoline in the bucket at time t, for t between 0 and 4, is given by a continuous function g, where t is measured in minutes. Selected values of g of t measured in pints are given in the table below. Use a midpoint sum with two subintervals of equal length indicated by the given data to approximate 1/4 integral 0 to 4 g of t dt. Using correct units, explain the meaning of 1/4 integral 0 to 4 g of t dt in the context of the problem. All right. So we're approximating 1/4 0 to 4 g of t dt using a midpoint sum with two subintervals going from 0 to 4. That means we're splitting up 0 to 4 into two pieces, from 0 to 2 and from 2 to 4. And we're going to use the midpoint in each case. So from 0 to 2, we're going to use this, the midpoint 1. And from 2 to 4, we're going to use the midpoint 3 here. Okay, so we have 1/4. I'm just leaving that where it is. And then each of these subintervals, 0 to 2 and 2 to 4, have length 2. So that's where the 2's come from. And we're using the midpoint, so we're going to take g of 1 and g of 3. All right, so just plug in those numbers. G of 1 is 2.2, g of 3 is 6.8. So we have 2 times 2.2 and 2 times 6.8. Add those up and divide by 4, and you get 4.5 pints. Okay, now the 1/4, the integral 0 to 4 g of t dt, that's an average value, right? So that's average value because we're multiplying on the outside by 1 over b minus a, 1 over 4 minus 0, or 1/4. So in the context of the problem, this integral is the average amount of gasoline in the bucket in pints over the time interval where t goes from 0 to 4 minutes. Right, it's worth just taking a second to look at the picture of this. What we did here is we took the interval from 0 to 4, we chopped it into two pieces, from 0 to 2 and 2 to 4. And in each case, we took the midpoint and we used the, we plugged the value of the midpoint into the function, right, 2.2, and we used that as the height of our rectangle. And for 3, we plugged in g of 3 to get 6.8, and that's the height of the second one. And then we added up the areas of these two rectangles. Consider the differential equation dy dx equals e to the y minus 1 times 2x cubed minus 5. Let y equals f of x be the particular solution to the differential equation that passes through 1, 1. Find y equals f of x. All right, so first I'm just going to separate variables. I'm going to bring dx over to the right and e to the y minus 1 over to the left. So we could do that a couple ways. We could divide by e to the y minus 1 and get 1 over e to the y minus 1, or we could multiply by each side by e to the negative exponent, which is 1 minus y, right? The negative of a minus b is always b minus a, so the negative of y minus 1 is 1 minus y. So that's the way I'm going to do it. I'm going to bring this to the other side by negating the exponent, which means it's e to the 1 minus y, and then I brought the dx over to the right. Now we're ready to integrate. So here there's a little substitution. If you let u equal 1 minus y, then du is negative 1 times dy. So we need a minus sign, and we undo that with another minus sign, and that's where this comes from. So we get negative e to the 1 minus y. This is just a power rule, 2x to the 4th over 4, which reduces to x to the 4th over 2. Antiderivative of negative 5 is negative 5x, and don't forget to add your arbitrary constant. Okay, we're now going to use the point to figure out what c is. So we replace x by 1 here and here, and y by 1 here. And just doing those computations, e to the 0 is just 1. 1 to the 4th is 1. 5 times 1 is 5. So bringing the 1 half and the negative 5 over, subtracting a half and adding 5, we get c equals negative 1 minus a half plus 5. 5 minus 1 is 4. So we have 4 minus a half, which is 3.5, or you could do it as 8 halves minus 1 half is 7 halves. So now we can go ahead and rewrite our solution here with c replaced by 7 halves. Okay, now it does say find y equals f of x, so we should get y by itself. I'm first going to eliminate this minus sign by multiplying by minus 1 on each side. So this becomes negative x to the 4th over 2 plus 5x minus 7 halves. And then if I take the ln of each side after doing that, then on the right we just get the ln, and here we get the ln of e to the 1 minus y, which is just 1 minus y. Subtract 1 from each side, and then we're going to negate each side. Again, the negative of a minus b is b minus a, so we negate the right just by changing this to 1 minus the ln of that expression. Okay, so the answer is y is 1 minus the ln of negative x to the 4th over 2 plus 5x minus 7 halves. Okay, the function little g is defined on the closed interval from negative 5 to 10. The graph of little g consists of 4 line segments and is shown in the figure below. That should say below. Let g be defined by capital G of x is the integral from 0 to x little g of t dt. Compute capital G of negative 5 plus g of 4 over capital G of 10 minus g of 7. Okay, we're going to do this in steps. First, capital G of negative 5, according to the definition, we're just replacing x by negative 5, little g of x dx. Now, since this is going in the wrong direction, right, negative 5 is smaller than 0, I'm going to interchange these, and whenever you do that, that negates the value of the integral. So this is the negative integral from negative 5 to 0 g of x dx. So negative 5 to 0 is going from here to here. Right? This integral is, we could compute that by taking the area under this curve here, which is a trapezoid, right? The trapezoid has bases of 1 and 3 and a height of 5. So it's 3 plus 1 over 2, right? We average the two bases and then multiply by the height. And don't forget that minus sign is still just sitting there. So 3 plus 1, that's 4 halves, which is 2 times 5 is 10. So that comes out to negative 10. Okay. Next, I'll go ahead and do g of 4. So that's the integral from 0 to 4 g of x dx. Well, that one's just a rectangle of length 4 and height or width 1. So that's just 4 times 1, which is 4. Now, g of 10 minus g of 7, that is the area under the curve from here to here. This part is going to be positive, and this part's going to be negative. So we have the integral from 7 to 10 g of x dx, which will split up into two pieces from 7 to 9. because that gives us the positive portion of the area, and then from 9 to 10, which gives us the negative portion. So for the positive portion, that's a triangle, right? So it's 1/2, 2 times 6. And this one's also a triangle. It's 1/2, 1 times 3, but we subtract that 1 because it's below the x-axis. Okay, so that's 6, 1/2, and the 2 cancel, we get 6. And here we get 1/2 times 3, which is 3 halves. So that's 12 halves minus 3 halves is 9 halves. All right, so we're ready to do this computation, just plugging in. G of -5 is -10. G of 4 is 4. So we get -10 plus 4. And then we have to divide that by what we just found, which is 9 halves. We can go ahead and take -10 plus 4 is -6. And we flip this and multiply to get 2/9. So that's -12 over 9, which reduces to -4/3. Okay. Just want to quickly look at the regions that we took the areas of over here. This was for G of -5, right? This one was for G of 4, and these two together were for G of 10 minus G of 7.